Senior Design Group C was sponsored by RV Intelligence, and our project was to automate an RV stabilizer jack for Husky towing products. Our jack can be controlled with switches and Bluetooth to create a user-friendly solution for many RV customers.
Hi, my name is Lucy Golovieski, and I'm a computer engineering major with a secure computing and networks minor. My ultimate career goal is to work with satellite communications, and this senior design project taught me a lot more about programming with embedded systems and how to never give up on a problem.
Hi, my name is Nader Abdurasul. I'll be graduating with a degree in computer engineering and a minor in robotics systems. My career goal is to work with autonomous systems. What I learned during this project is to put assumptions aside and be more methodical with my troubleshooting. I've also gained a lot of experience with embedded coding.
My name is Andrew Melvin. I will be graduating with a degree in electrical engineering with a double minor in robotics and physics. My ultimate career goal is to work in medical robotics. What I would say I took away from senior design is hands-on, practical board-level design and troubleshooting experience.
My name is Isham Zidan, and I'll be graduating with a degree in electrical engineering. My main career goal is to work in power systems, specifically distribution system and substation design. The biggest lesson I learned in senior design is attention to details.
We designed a 4-layer board. The top and the bottom layers are for power. The second and the third layers are for signal. The board has a length of 16 centimeters. The upper part of the board has a width of 7 centimeters, and 6 centimeters down from the top, the width is increased to 8 centimeters. We designed the board so that the power supply will be connected to the bottom right of the board. We placed the TLE driver as close to the middle of the board as possible, so it's close to the FETs at the top and the radio at the bottom. We placed the radio at the very bottom as far from the high current as possible to avoid any radio interference.
Here you can see our board installed face-up for hardware testing purposes. The board we created needed to be able to fit into current models of the Husky Jack as to be a quick plug-and-play upgrade to the former board's design. In having this plug-and-play criteria, our board would need to be able to operate the manual switches installed on the jack. Through simple soldering to a mating connector, we were able to demonstrate full functionality of the switches, which includes extend and retract of the motor, showcased here, as well as LEDs and a work light. The board needed a few slight hands-on modifications to allow intended operation, which included the removal of diodes interfering with signal outputs, jumping 12 volts past the component giving us an unintended fault error, as well as correcting a power error by jumping 3.3 volts from a resistor to the Hall effect sensor, seen here.
Our project is not only controlled with switches. We can connect to the jack via Bluetooth to send different commands wirelessly. In this video, you can see how excited I was when we first achieved the Bluetooth connection. When the correct command is sent, the jack will extend, stop, retract, or control the lights. The commands are sent back and forth using the GATT protocol. Our code takes in these commands and calls different functions based on the code received. Working on the Bluetooth was a great experience to use in future applications. Achieving the initial connection was the most difficult part of this task. Once we were able to connect to our PCB, we were able to call the functions we wrote previously for the motor driver.
To control the lights, we can use the two physical switches attached to the jack. One switch controls the work light, and the other switch turns on and off the RGB lights. The RGB lights will have the color and mode they were last configured to by the user through the app.
We can also use the Bluetooth connection to control the lights. Customers can turn on and off a work light for their workstation, or use RGB LEDs to light up their RV. The user can send different color commands for their customized colors, so we are demonstrating the command to cycle through all of the different colors. We have an accelerometer in the PCB to detect motion and display orientation data. When the PCB moves, a new motion interrupt is sent to the Cypress module. You can see the motion interrupt displayed through UART on the screen. Our output data rate is set at 25 Hz, so new orientation data is sent to the Cypress module every 40 milliseconds. This flashing light represents new orientation data, while the flicker of pink represents motion. This is the development board for our accelerometer. Before we had our PCB designed, the software team used development boards to test our code. Each of us had a Cypress Bluetooth board to connect to the different modules. The Bluetooth development board easily connects to the Cypress Mini-Prog debugger. This debugging equipment was essential to testing our code.
We had the dev board for the TLE connected to a logic analyzer, which allowed us to see exactly what we were sending and getting back through the SPI lines, making sure our code was sending the right commands to the right registers. Once we had our populated PCB, we tested the TLE by having it drive a small motor while we slowly increased the current supplied to it, making sure that everything was working as intended and that we weren't getting any errors. Then we slowly decreased the current to make sure that the motor slows down and eventually stops with no issues.
This is how we tested the Hall effect sensor. By spinning the magnets around and monitoring the pulses, we were able to determine the direction, speed, number of revolutions, and position of the motor. Since the magnets are placed about 120 degrees apart, one pulse is always shorter than the other. This is how we determined the direction of the motor. There were many successes in this project, but solving our problems created the biggest learning experiences. Pulse width modulating the LEDs and coding the accelerometer was troublesome, but the team was able to work together to form a solution. Since we also had a few problems on the PCB, it did not seem safe enough to lift the full load of an RV. While we were able to fix these problems by adding and removing components, the system did not seem stable enough for a large load.
Our motivation for this project initially came from our desire to gain real-world experience in engineering. We chose a sponsored project to learn how to produce a working product that fits the customer's requirements within a time constraint. Working on this project allowed us to develop new skills individually and as a team that will be invaluable in our careers.
What mainly helped us collaborate creatively and achieve successful teamwork is accountability. Through task coordination and communication, there was always a team member working on an aspect of the project needed to make meaningful progress and maintain time constraints. If at any time a team member had an issue, the whole team collectively joined in to overcome the dilemma with logical insight and diligent work, which resulted in a functional solution.
One of the difficulties that we faced is that the scope of the project changed due to the sponsor losing his customer for the proposed project. Fortunately, the sponsor was able to recast the project with another customer, with extremely similar topology that required us to rescope, research, and perform new set of requirements. Although similar, the time constraint made it even more challenging.
Our team was motivated to stay focused because we wanted to see the outcome of our hard work and see the impact of the skills that we gained through this journey. We used this motivation to persevere through the difficult problems we faced to create a working project that we are very proud of.